Hello, this is David Bridges. This is Unit 1, Lecture 3 of Intro to UAS, History of Unmanned Aircraft Systems, Part 1. And what we're going to be doing in this lecture is we're going to survey the history of unmanned aircraft to illustrate the technological developments that made unmanned aircraft possible. In other words, we will trace the history of unmanned aircraft, and in doing so, you'll see the different technologies that were developed so that we eventually got to the point where we are today. So the goals are to understand the development of the technology and to understand the applications of unmanned aircraft that resulted. Not only the fact that we could fly the airplane, but also some of the things we could do with the airplane once we flew it. Okay. So we're going to consider unmanned, self-propelled winged vehicles. I'm only going to talk about basically one helicopter unmanned aircraft. The rest of it will be winged, fixed-wing aircraft. The earliest example that I'm going to use was a scale model of a manned aircraft, and we'll talk more about that later. The earliest UAVs were aerial bombs or torpedoes used to attempt to blow things up. During World War II, the emphasis became creating drones for target practice so that we could practice anti-aircraft gunnery. Then after World War II, there was more development of target drones, and then some of the first observation/reconnaissance drones. That became a focus. Now, the aerial torpedoes later progressed into cruise missiles, which have been used for some years now, and I'm not going to talk about those here. That's a separate category. We're going to attempt to focus on aircraft that have at least some self-controlling mechanism. So if you're basically, a model airplane that you fly manually by remote control all the time, these days, now early on, yes, unmanned aircraft, but these days, unmanned aircraft have really advanced beyond that. So we will make a few exceptions, as you'll see. Okay, so again, this is more or less my definition, but if we go back to basically the beginning of manned flight period, powered flight period, we go back to someone named Samuel Pierpont Langley. He was the secretary of the Smithsonian Institute, the head of it. He was trying to develop a manned aircraft, and he was doing it at the same time as the Wright brothers. Now, he was generous. He also, they wrote the Smithsonian, asked for reports on, whatever had been done on flight, and he provided them what he had. But he was working on his own airplane, trying to develop his own airplane. And to begin with, he built a quarter-scale replica that flew unmanned over the Potomac River. Here's a picture of the model in the shop and in flight. It was steam-powered. In 1896, model number 5, the unpiloted number 5 unpiloted model flew nearly 3/4 of a mile after a catapult launch from a boat on the Potomac River. Just straight ahead, but it was stable flight, and it flew. It was powered. Just didn't have anybody on it. 10 times further than any previous heavier-than aircraft had flown. Now, the interesting thing is the picture of it in flight was taken by Alexander Graham Bell, who went on to invent the telephone. Actually, may have invented the telephone at this point. He also was interested in photography, so he took this picture. Now, Langley built the bigger, the full-scale manned version of this, tried launching it off the houseboat in the Potomac River, tried twice, both times it crashed, basically just fell right into the river. And then before he could try it again, the Wright brothers took off and flew, and so they basically won the competition. Now, some years later, a guy named Curtis came back and made some modifications to Langley's airplane and was actually able to fly it. That led to a dispute between the Wright brothers and the Smithsonian because they said, Langley developed the first manned aircraft. Well, He developed it, it just didn't fly, and it didn't fly until Curtiss made a whole bunch of modifications to it. But anyway, so back to the point of the lecture. To me, this is really the first unmanned aircraft. It's powered, fixed wing, flying on its own, no manual control by anybody while it's in the air. Okay, it was stable, and you can make a stable airplane. If you've ever made a paper airplane, typically they're stable. They fly in a straight line. They recover. They don't, if they stall, they recover. So you can make something that will fly. The problem is, how do you make something that will basically stay on course? If you're flying an airplane, like a paper airplane, you throw it and there's a wind blowing perpendicular to the way you're throwing it, it's going to move off. How do you keep an airplane on course? Okay. So it was very early on. Remember the Wright brothers flew for the first time in 1903. Well, not too long after that, people developed the first autopilots. And what they did was allowed the airplane to continue flying in a single direction, not being blown off course by the wind, and maintaining orientation. We'll talk about that in just a minute. So in 1908, this guy named Elmer Sperry developed a gyrocompass, which is a compass, but it doesn't rely on magnetism. It relies on it's a gyroscope, it's a great big spinning gyroscope, and it relies on the concept of precession and the Earth's rotation to find true north. This was used in the Navy because ships are made out of a lot of metal, a lot of steel surrounding, the compass, and so that can really mess up a magnetic compass. But the gyro compass, that's not an issue, and so in 1908, Sperry is already working on this idea of using gyroscopes to give information. In 1912, again only 9 years after the Wright brothers, he developed his first autopilot and demonstrated it in 1914. His son, Lawrence Sperry, actually did the flying, helped with the design and did the flight testing. And you'll hear Lawrence Sperry's name a lot because he continued the business after his father. Now, so the fundamental idea of a gyroscope is why it works to do what it does is once you get it spinning about its axis, it doesn't want to rotate about an axis perpendicular to the spin axis. So let's say you have this is why bicycles work, okay, while they're stable. If it's spinning, say the bicycle wheel is spinning about the axle, right? Well, if you try twisting while it's spinning, if you try twisting the wheel about, an axis perpendicular to the axle, like turning the wheel or whatever, it's resistant to it. It doesn't want to do it. If you've ever spun a bicycle wheel, pulled it up, we're sticking up in the air, and then rocked the handlebars back and forth, you can feel the resistance. That's due to the gyroscopic effect. Okay. So what they would do is they would take this gyroscope and mount it on a gimbal, which is a frame that's free to rotate basically in all directions. So, and then you attach that gimbal to the airplane. Well, you do it in such a way that the gyroscope always maintains its same orientation. Say it's spinning about a vertical axis. So it's spinning, and the axis it's spinning about is pointing directly up. Well, the airplane may move around that, but because it's mounted in this free-to-move gimbal, the gyroscope always maintains the same direction. Okay, and then you can use that relative motion between the gyroscope and the airplane to do things. And what Sperry did was take these gyroscopes, connect them to actuators, which were in turn connected to aircraft control surfaces. All right, so here's an example. So this is the green cylinder at the right-hand side is a gyroscope. It's spinning about a vertical axis, okay, and then it's mounted in this gimbal thing. So that's always going to stay sticking straight up, all right, unless the airplane does something really violent, it's going to be sticking straight up. But let's suppose the airplane banks. One wing goes down, one wing goes up. Well, the gyroscope stays vertical. The airplane, this frame moves around it, and so what that does is it rotates that little pan there below what are called the air jets. This was in Sperry's original system. Well, by changing the air jet flow, you would change because this plate would rotate back and forth. Well, that would change the air pressure, which was then sent to an oil pressure barrier. It's something that could vary oil pressure. When that oil pressure changed, then it would move a piston in a hydraulic cylinder. So that's the object at the left with the double arrow. That cylinder, that piston was then connected to a control surface, and we'll see the whole thing in just a minute. But basically, it was designed such that if say the airplane banked right, so the right wing went down, the left wing went up, the gyroscope would stay vertical. This thing was designed so that it would deflect the ailerons and cause the airplane wings to come back level. Okay? So the whole system, and we'll see it in the next frame here in a minute, but the whole system was basically maintain a particular orientation, particular attitude. All right, and so here is the complete autopilot, schematically at least. You only need two gyroscopes because not only will the vertical gyroscope handle roll if one wing goes up or down, but it'll also handle pitch if the nose goes up or down. And you see there are two different rotating assemblies there now. The one for the roll that we just talked about, and also the one in the back for the pitch. Okay, and so you'll see that the vertical axis gyroscope, the top green cylinder, is connected to both the aileron, which controls the roll, and the elevator, which controls the pitch. Okay, and so again, if the airplane tries to move, tries to have some other orientation other than wings level, nose level, then it moves around the gyroscope. It causes these plates to rotate, changes the airflow, changes the oil pressure, moves the piston, moves the control surface. Now the bottom one, the bottom gyroscope, the bottom green cylinder, it's rotating about a horizontal axis that is pointing basically along the axis of the airplane, and that's the one that controls yaw, whether or not the tail goes left or right, or the nose goes left or right. Okay. Now it would also, if you needed to, you could also use it to handle pitch, but we've already got pitch handled by the other one. Yeah. So the horizontal rotation axis gyro basically handles the rudder, it handles yaw. Okay. So the whole system then was developed. Again, notice there are no electrical circuits. There's no wires. There's no battery. There's no generator. This is all what's called analog. It's all hydromechanical. Okay, there's air pressure changing, oil pressure changing, all that, but nothing nothing that involves any kind of electricity. Okay, now, so the way he demonstrated this, so Lawrence Sperry, test pilot, gets in the airplane, takes off. It's a biplane. And he's flying it, so he turns on the autopilot. And he gets up out of the cockpit and walks out one of the wings. Now you've got a 150, 100, I don't know how much the guy weighed, but probably in the vicinity, say 180 pounds, standing on one wingtip. Well, that's going to want to cause the airplane to roll, right? If he goes out the right wing's going to want to go down. The left wing is going to want to go up. The autopilot corrected for that and maintained the wings level. And sure, of course, he's flying by a crowd of people when he's doing this, okay? But that's the way it was demonstrated. That's the way it worked. Okay? Now, that system was first put into this airplane for the purpose of an unmanned aircraft, okay? They started in 1916. World War I was going on in Europe. The United States hadn't gotten involved yet. But they They wanted to develop basically what they called an aerial torpedo. Again, this was basically going to be a flying bomb. The autopilot was basically to make sure they would point it in some direction and then make sure it flew straight in that direction until it got to its target. Okay. Well, they tested this thing several times. They only had one successful flight in 1918. They tried launching it from the rails, and then things happened, and then they launched it from the top of the moving car, and they finally got a successful flight out of it. Now, March 1918, this was the first time a full-sized, automatically controlled unmanned aircraft had actually flown. Okay, so this is not the Langley, which was just stable. It didn't have an autopilot in it. This was the Curtis Berry aerial torpedo was an autopilot stabilized aircraft. You see how big it was, wingspan 22 feet, top speed 70 miles an hour, weight almost 1,000 pounds. It wasn't a small little airplane. Okay, now on that subject, we're going to be talking a lot about aircraft dimensions because I want you to have an idea of the size of these things, how big they are, and so forth. So, so here are some dimensions that we'll be keeping up with. So first of all, wingspan B, the symbol we typically use for the wingspan is B, and that's just the distance from wingtip to wingtip. Okay, so it tells you how wide the wings are. H is the height of the aircraft, L is the length. Now there's another area, there's another dimension, an area that will become important later that we will make use of sometimes. And so that's something called the planform area, which is basically if you look at the wing from the top, you see what's called the plan view or the planform. The area of the wing that you see is referred to as the wing planform area and given the symbol capital S. We generally consider the wings basically being carried through the fuselage. So you imagine the wing going all the way to the center of the fuselage without the fuselage being there. And that's what we consider the planform area of the wing. Okay. So the wingspan, the planform area, and the maximum gross takeoff weight, MGTOW, just max takeoff weight, are numbers that we typically use to characterize the size of an aircraft. So just some aircraft you might have heard of. The Cessna 172, general aviation, length 22 feet, wingspan 36 feet, maximum gross takeoff weight 2,400 pounds. Okay, lighter than a car. Okay, you go down the list, you go all the way to a Boeing 747 commercial airliner. Now the length is 250 feet, the wingspan is 224 feet, planform area almost 6,000 square feet, and the maximum gross takeoff weight of 975,000 pounds. And there are some aircraft that weigh over 1 million pounds and do have a maximum gross takeoff weight over 1 million pounds. Okay. But these are just some typical numbers. The F-15, which is a fighter, 63 feet long, 42.8 foot wingspan, 81,000 pounds maximum gross takeoff weight. So just some numbers of manned aircraft, some that you might be familiar with, to give you kind of a reference point when we talk about these other aircraft. Okay, so the next controlled unmanned aircraft was the Kettering aerial torpedo, or the Bug. All right. Again, the idea of launching it, basically extending the range of artillery, basically carrying a bomb further than you could shoot it with a gun, and also a heavier load than you could carry with a manned aircraft. Really, heavy bombers were not, they were beginning to be developed, but they weren't quite there yet. So, you know, so the idea, okay, of a torpedo, this aerial torpedo, it's powered by one 4-cylinder, 40 horsepower engine. It was basically one-time use, so it was constructed of wood laminates and paper mache, while the wings were made of cardboard, right? But it had a Sperry autopilot in it. Total cost per plane was $400. This is about 1917 when this thing went into production or was being developed. It didn't get developed before the end of World War I, so they built some and then it didn't go into full production. But what they would do is that they launch it, it'd fly, it would maintain its direction, maintain its course because of the autopilot on board. And there was a timer that was connected to the propeller. And so when the propeller completed a certain number of revolutions, that would mean it had flown a certain distance. So we'd say, okay, I'm there. So there would be bolts. The wings were attached to the fuselage by these bolts, which would basically be retracted, so the wings don't fall off. Wings do not fall off of airplanes in flight. The only reason the airplane is flying is because the wings are holding it up. So the wings can't fall off in flight. If they could, you wouldn't need them. This is a pet peeve of mine. I've been doing aircraft for a long time, and so I always cringe when I hear the wings fell off the airplane. No. But these, so basically the wings would separate, the fuselage would drop, the warhead was in the fuselage, and then it would just hit the ground and explode. Okay. So you see it carried a 180-pound warhead, 12.5 feet long, 15 feet wingspan. You see in the lower picture the size of it. 530-pound loaded weight, cruised at 50 miles an hour, and had a range of 75 miles. And there are actually videos, if you use this link, there are actually some videos of this thing, movies that were made of it when it was in flight, which is actually kind of impressive considering it was about 1919, 1920. Not a whole lot of air-to-air footage at that time, and these are air-to-air pictures. So I encourage you to take a look at that when you get a chance. Okay, now the British were also working on an aerial torpedo concept a little bit later. This is the Larynx. It was an anti-ship weapon. Again, had an autopilot in it developed by a British professor, Archibald Lowe. Could fly 200 miles an hour and a range over 100 miles. And they did do some tests, and it did come really close to one target. So that was generally considered a success at the time. It didn't really go into production, but you know, it was considered reasonably successful when it was being flown. Okay, now we talked about this before when we talked about where the term drone came from. Well, this is the British version that the American officer went over to review and then came back and directed his subordinate to come up with a similar program. So this was the radio-guided version of the de Havilland Gypsy Moth, and it was called the Queen Bee, and used for naval anti-aircraft gunnery practice. So it launched this thing, they fly it by remote control. You see there in the upper photo the guy changing the controls for the aircraft as it's flying overhead. The lower photo is basically been mounted on a launcher, basically has sailplane floats on it, so it can land on water. That's about to be tested. You see the man standing there. The man in the front with the top hat is Winston Churchill. You may have heard of him. If not, you should. Churchill, British history. He was a big deal. But so it's a full-size airplane, 23-foot length, 29-foot wingspan, 1,825-pound loaded weight. Could fly 109 miles an hour. Could fly for 302 miles. So you see all the specs there, and you know I think it was successful for the time. It started in 1935 and used by the British for the ships to practice anti-aircraft gunnery. Okay, so we continue with the target drone thing now because we're moving close to World War II. We haven't gotten there yet, but 1935, Reginald Denny, who was actually an actor. He was in British and American productions. I can't remember now if he was British or American himself, but this was developed in America. But he was an actor, but he got involved in this. And so he came up with this RP-1, and it was the first aircraft designed to serve as a target drone from the beginning. You know, not an adapted airplane from somewhere else, but from the beginning. And it was marketed to the Army, went through different variants, and then finally developed the RP-4 in 1939, which the Army bought and designated the QC-1. Then went to the QC-2, and then there were other variants after that. Now, the U.S. Army Air Force at the time, and during World War II, the Air Force wasn't separate. It only became separate after World War II. So the U.S. Army Air Force and the U.S. Navy fought almost 15,000 target drones from radio planes during the war. In the lower picture, you see one about to be launched. I think it's a QC4. I'm not sure. It's either QC4, QC2, or QC4. The fuselage is a little bit different. We'll see that in the next slide. But so there it is. It's about to be launched on a ship. So you see the sailor getting it ready for launch. So you see the sizes. Length about 8 feet, wingspan 12 feet, depending on the model. Max speed 85 miles an hour. It could stay in the air for an hour. Okay. Radio control. Now see, the deal is, it took a while for radios to get small enough to mount in things like remote control aircraft. So radios were big. You rarely saw them in World War I aircraft because they were so big, and the batteries that they took, or the generators, were so big. So it just took a while for radio technology to get small enough to be mounted into an aircraft. Now, this is also about the time, basically right before, during World War II, about the time that basically radio control model airplanes started becoming popular. Okay, so here's the QC4. So it has this V-shaped fuselage, which you see here in the one on the ship. And then you see one that's been used. It's actually been shot down. So it's going down. It's on fire. It's basically got a fabric covering over a wooden frame, and the fabric is just about all burned away, so you can see the frame. But there it is, fulfilling its function. Now, just a little bit of trivia, nothing serious here, but their factory was in Van Nuys, California. And in 1944, a U.S. Army photographer named David Conover was sent over to photograph the radio plane factory, basically where they're putting things together. And he finds this woman. Her name was Norma Jean, and took a picture. She was working on assembling these aircraft. You see her there, with a propeller posing, but she was actually working on assembling these aircraft. And he was a photographer, so he said, well, you've got potential as a model. So I think he gave her a business card, put her in touch with another photographer. Well, she became famous, eventually became an actress, and changed her name to Marilyn Monroe. You might not have heard of Marilyn Monroe. Your parents may have. Your grandparents definitely have. So we can thank the unmanned aircraft industry for Marilyn Monroe. Another little bit of trivia. The Army photographer that was sent over by an Army captain named Ronald Reagan, who would go on to become President of the United States in 1980 and be reelected in 1984. Okay, so another target drone, another one developed from a full-size aircraft. This was the N2C-2 target drone developed by Curtiss. The basic aircraft was developed as a trainer in the 1920s. In 1937, they developed a radio-controlled version of it, again, for use as a target by anti-aircraft batteries. Now, it was controlled from another aircraft. It's called the TG-2. It was in service by 1938. Now, I'm sure that if you were the pilot of the TG-2, you made sure there was plenty of separation between you and the target drone, and you made sure everybody on the ground knew which of the airplanes they were supposed to be shooting at, right? Okay, so you see how big it is. Again, it's a big airplane, 39 feet, 2-inch wingspan, gross takeoff weight 2,832 pounds, range 366 miles. Don't have an endurance there, but several hours in the air. Okay, so that was just a target drone. Okay, now we are going to talk about the beginnings of cruise missiles, and basically, the bug was basically an aerial torpedo, a cruise missile, basically. Well, the Germans developed the first jet-powered cruise missile. Now, it was powered by pulse jet. We'll talk about that in a little bit. They started flying these things in 1942. The fuselage was made out of steel. The wings were built out of wood. So they had a weighted pendulum system to provide fore and aft attitude measurement. that controlled the pitch, where the nose went up or down. Then a gyro compass and a magnetic compass together were used to control roll and yaw. That was that would basically keep the airplane on the correct heading. There's a little propeller on the front. Again, we're at this business with propeller, and when it had turned a certain number of turns, every time it turned 30 revolutions, the counter would go down by 1, and when the counter got to 0, that meant it was basically over its target. And so, again, we have bolts here, but these were detonating bolts. 2 spoilers on the elevator were released, so all of a sudden you got a lot of drag on the elevator, which is the back surface. The linkage between the elevator and the servo was jammed, and a guillotine device cut off the control hoses to the rudder servo, setting the rudder neutral. So all this stuff basically meant that the V1 went over nose down in a steep dive. So basically it maintained its heading, but just dove very steeply. It presumably tried to hit its target. They weren't extremely accurate. They're basically referred to as terror weapons because the primary purpose was psychological. They did damage, but they did damage to cities. So they killed and hurt people, but they didn't knock out important factories or anything like that. So they were basically just weapons against the civilian populace. Okay, so pulse jet, interesting device. Basically, it's a cyclic jet engine. So some fuel is injected and some air is drawn in, and then the fuel is ignited, so it explodes. Now, these vanes that let the air come in on the left are basically forced shut. So you get the pressure pulse that comes from this explosion pushes against the front of the engine, but there's no pressure resistance to the back, so you get a push toward the front. So you get a thrust push. And then the products of combustion are exhausted, and when they're exhausted, this outflow causes the vanes to open again, and then more fuel is injected, it explodes, the vanes are pushed shut, there's a little pulse of thrust to push the plane forward, stuff goes out the back, the vanes open again. So this goes over and over and over, but it happens very rapidly, so 50 times per second. Now all this has to be tuned very precisely. The length of the engine and all this other stuff is tuned very precisely, but when it works, you get thrust out of it. Now they're very loud, and because of this oscillating, that's where the aircraft actually got its nickname, the buzz bomb, because this thing is oscillating, vibrating. Okay. Launched from a steam catapult, you see that in the lower right-hand picture, this long gantry. This is one that's preserved maybe in France, because that's where they built the launchers in France, and they were launching them toward England from France. But I'm not sure exactly where this one is preserved. It may be in England, just in the museum. 4,700 pounds, big, had a warhead weight of 1,900 pounds. That's a pretty big bomb to be carrying. Had a 160-mile range, so it could get over the channel, get over the English Channel, and hit London and other targets in England. Flying 400 miles an hour, which was on the high end for piston engine fighter aircraft at the beginning of the war. Later, when the Spitfires came online, and they were actually there early, but some of the other aircraft, particularly the Spitfires, could fly as fast as these things. And they discovered that what they would do is they would try to catch them before they went into their dive, and they would basically tip them over. They would fly, basically put their wing under the V1 wing and then flip it over, and that would just mess up its guidance system, and so it would just crash into the ground there. So they'd try to intercept them before they reached populated areas, tip them over, and cause them to crash into the ground. They would explode and there'd be damage, but if they were outside of populated areas, that was okay. Okay. So we've done targets, We've done aerial torpedoes. We did aerial torpedoes and targets and an aerial torpedo again. Now we're going to look at an example of one of an unmanned aircraft that was specifically built for observation or surveillance. Okay. This was the RP-71 Falconer, developed by Radioplane. They stayed in the business, and eventually they were actually bought out by Northrop. Okay, so they were a successful company, and eventually were bought out by another successful company. You see the white objects alongside the fuselage under the wings. Those were rockets. This was rocket-assisted takeoff. So basically, be put on a stand, what was called a zero-length launch, that it could be launched without having to have a runway, and then was recovered by parachute. It's under radio control the whole time. It had I believe it had a still camera system. It would fly over somewhere, take photos on film. I know some of you may not even be familiar with this concept of film, but that's the way cameras used to work. There was a stuff called film, and you would shine light through a lens on the film. You bring it back, you develop the film, and then use the film to make prints. So it was kind of a laborious process. It took a while, but this was, one of the first applications or first uses of unmanned aircraft for reconnaissance. Go out and look what's going on out there and come back and bring us a report. 13-foot long, 11.5-foot wingspan, weight 430 pounds, kind of heavy given the size. Speed 185 miles an hour, could fly up to 15,000 feet, stay in the air 40 minutes, okay, and go out 100 miles. Now, let me step back on that just a minute. Often in these things, the range is dictated by the radio link and not the actual performance of the airplane. For example, our RS-16, our actual range is dictated by how far out it can go, and we can still talk to it by radio. Now, we operate the RS-16 at under 1 watt transmission power for the radio. If we went to the FCC and got a license, we could get an amplifier, maybe go 5 watts, and then that would allow us to go further out. So you have to be careful when you're looking at these things, when you look at the term range, because for manned aircraft, range just means how far you can fly the thing before it runs out of gas, whereas with an unmanned aircraft, range may mean how far it can fly. It may mean how far it can fly and still be in radio contact. So you just have to be aware of that distinction. Okay, now another application, which came along about the same time. The Falconer, the one we just talked about, was about 1955. Okay, so B-52s, large, very large bombers. They were used in the Vietnam War. A lot of them were getting shot down by the surface-to-air missiles by the North Vietnamese. So the Air Force McDonnell Aircraft Corporation came up with the ADM-20 Quail, which was a radar decoy. The way it was built, it would basically have the same radar signature or the same radar cross section as a B-52. If a radar painted it, that's the term that's used, if the radar beam hit it, then the reflection coming back, they would say, oh, it's a B-52, when really it was just this thing. And in the next slide, I'll show you the relative sizes. Now, it had an autopilot integrated with a rate integrating gyroscope, and we'll talk more about that later. Basically, you could detect the rotation rates of due to the precession of the gyroscope, and then you could integrate that in time to get angular position, so you could get heading. This thing could be programmed to execute 2 turns and 1 speed change during a flight time of 45 to 55 minutes. So it could, basically look like it was going somewhere. You wouldn't just drop it; it would just fly straight. It would actually look like it was following some kind of mission profile. Carried in a B-52 bomb bay and then launched during flight. Okay, so here's the picture of the aircraft, of the Quail being launched. You can see the relative sizes. It is considerably smaller than the B-52, but it has the same radar cross-section, the same radar signature. Okay? heavy, 1,200 pounds, but it was stubby, basically built to be dropped from a bomb bay. But because it had all these straight edges and everything, it had this large radar cross-section. Now, remember, it's supposed to look like a B-52 to a radar operator, which means not only does it have to have the same size, it also has to have the same performance. Okay, when it starts flying, it needs to look like it's flying like a B-52. Okay, because if all of a sudden it's flying a lot slower and lower, and so well, that's weird, but we know which one's the B-52 because it's flying at 50,000 feet and it's flying close to Mach 1. Well, this Quail had to fly that. So it could fly at an altitude of 50,000 feet, which is where the B-52s flew, and it could fly at a Mach number of 0.9, which was close, basically about the same thing as the B-52 at that altitude. Okay. So basically the idea was it's a radar decoy. The tracking radar on the surface-to-air missiles will lock onto this instead of the actual bomber. If this thing got shot down, well, you don't lose a crew, you don't lose a big bomber, you just lose one of these drones and one of these unmanned aircraft. And so that was one particular, and there were other variants, but this was or other types of similar types of drone decoy aircraft, but this was the primary one. So, okay, so that's the end of the lecture, and we will continue. The next lecture, we will continue to look at the development of the history of the development of unmanned aircraft. Basically, we'll continue with the history of their development. That concludes the lecture.